Hello students, welcome to Achievers India. To introduce myself, I am Siladitya Mukherjee. You can call me Siladitya sir or SM sir. So we will be starting with the number systems. So in total, defining the number systems, first we will be just discussing about the decimal number system, and then we will be evaluating the other number systems with respect to the numbers given in decimal number system. Let's have a look. So here we will be generating three different number systems with respect to decimal number system. The binary number system, octal number system, and hexadecimal number system. So in decimal number system, we represent the different digits, the power of 10. Similarly, in binary number system, we will be representing based on the digit 2. In octal number system, we mean the digits are based on 0 to 7. Octal meaning 8 digits that we have. And hexadecimal number system, we will be having the power of 16. Over here, first let's have a look at how we define the numbers based on decimal number system. So since we have already learned this from childhood, we can define the numbers within seconds. So decimal number system, if we start from 0, 1, 2, 110 to the power 1, we have written 1. So the number of digits is 0 to 9. And after that, the number of digits, we are continuing with 0 to ... 9. So we have written up to 16. Over here, if you put imaginary zeros, after imaginary zeros, we can have, after completion of 1, we will be continuing with 2, 3, up to 9. So that will represent 10, 20, 30, up to 99. So after 99, what happens? We start with 00, and before 00, we put 1 under 10 to the power 2, and so on. So it becomes 100, and then we can continue with 00299 after 1. Then after 2, we can continue 00299. So that becomes 299, 200 to 299, 300 to 399, up to 999. Now in binary, we can represent 0 as 0 and 1 as 1. So 2 can be represented as 1, 0, because we have only the binary digits, that is 0 and 1. Binary means 2, so we will be having only 2 digits that we can represent in binary number system. Similarly, in octal number system, 8 means 8, so we can represent only 8 digits, that is 0 to 7, and so on. In hexadecimal number system, we can represent 16 digits. Now how many digits we have? 0 to 9. So from 10 to 15, we represent the hexadecimal digits as capital A, capital B, capital C, dot 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 dot, capital F. So 10 is represented as capital A, 11 is represented as capital B, 12 as capital C, 13 as capital D, 14 as capital E, and 15 as capital F respectively. So we will be trying to depict all the number system based on the decimal number system, which we all know. So here, as we can understand, binary can represent only 0 and 1. So under 2 to the power 0, we will be having 0, and under 2 to the power 1, we will be having 1. So 2 to the power 1 is 2. So under 2 to the power 0, we won't be having any digit. So simply it defines 2. 3 is represented as 1 and 1. Why? Under 2 to the power 1, we have 1, and under 2 to the power 0, we have 1. So 2 plus 1, that is 3. So 1, 1 represents 3 in this manner. 4 represents 1, 0, 0. How? Under 2 to the power 2, we have 1. And under 2 to the power 1 and 2 to the power 0, we have zeros. So 2 to the power 2 is 4. So we can represent in binary, the binary equivalent of 4 is 1, 0, 0. Similarly, 1, 0, 1 is represented based on 5. 6 is 1, 1, 0, that is 2 to the power 2 plus 2 to the power 1. 4 plus 2, that is 6. So 1, 1, 0. 7 is 1, 1, 1. So 2 to the power 2 is 4, 2 to the power 1 is 2, 2 to the power 0 is 1. So 1 plus 8 is 2 to the power 3. So 7 is less than 2 to the power 3. So we won't be having any digit under 2 to the power 3. We are having digits under 2 to the power 2, 2 to the power 1, and 2 to the power 0. So that is 1, 1, 1. So 1 represents 2 to the power 2, this one represents 2 to the power 1, and this one represents 2 to the power 0. So 4 plus 2 plus 1 is 7. 8 is represented as 1, 0, 0, 0. 1, 0, 0, 0. Under 2 to the power 3, we have 1. So 2 to the power 3 is 8. 2 to the power 2, 2 to the power 1, and 2 to the power 0, that is 4 to 1 will be 0. So it is 8. Since we are having 2 to the power 3 as 8. So 1 means 2. So binary represents 1 and 0 in place, that is true and false. So true means 1, false means 0. So similarly, 9 will be 1, 0, 0, 1. 10 will be 1, 0, 1, 0. 11 will be 1, 0, 1, 1. 12 will be 1, 1, 0, 0. Because 2 to the power 3 is 1, 2 to the power 2 is 4. So 8 plus 4 is 12. So rest, we don't need any bits. Bit is binary digit. 13 is represented as 1101, 14 as 1110, 15 as 1111. So 16 is 2 to the power 4. So under 2 to the power 4 we will be putting 1, and rest of the 4 digits will be 0. So this is how we represent 16. So this is the binary equivalence of the different decimal numbers that we have defined over here. I have given an arrow from the number so that it is convenient for you to understand which one equivalent is which one. So 5 equivalent is 101, 2 equivalent is 10, and so on. Now we come to octal. So 0, we have 0, 1 means 1, 2 is represented as 2, 3 is represented as 3, 4, 5, 6, 7. So up to 7, we can just represent it as 0 to 7, because in octal we have 8 digits, as I already explained. So 0 to 7 are 8 digits representing 0 to 7. So 0, 1, 1, 0, these are the binary equivalents up to 1, 1, 1, and these are the octal equivalents. So 8 will be obviously represented as 8 to the power 1. Under 8 to the power 1 we will be having 1. So under 8 to the power 0 we will be having 0. So 1, 0 is the equivalent octal number whose value is 8. So 1, 0 is the equivalent number in octal. Is it clear? So 9 will be 1, 1. 10 will be 1, 2. So 1 means 8 to the power 1 is 1, 8 to the power 0 is 2. So 8 plus 2 is 10. So similarly 8 plus 3, so 1 under 8 to the power 1, 3. So this is 8 plus 3, 11. So 1, 4 is the equivalent octal for 12. 8 plus 4, 12. Similarly 13 is 1, 5. 14 is 1, 6. 15 is 1, 7. So under 8 to the power 1 we will be having 2. So what we mean by 2? 2 into 8 to the power 1. I repeat, what is 8 to the power 1? 8 to the power 1 means 8. So 2 into 8 to the power 1, because in octal we can represent 2 up to 7. So 2 is written under 8 to the power 1, and then 0 under 8 to the power 0. Alright. So let's write these things in sequence. So this is 7, then 8 is 1, 0, 1, 1 is 9, 1, 2 is 10, 1, 3 is 11, 1, 4 is 12, 1, 5 is 13, 14, 1, 7 is 15, and 2, 0 is 16. So 2 into 8 to the power 1 is 2, and 0 under 8 to the power 0. So if you give 7 under 8 to the power 1, that means 8 into 7. 8 sevens are 56. And then 7 under 8 to the power 0. So 56 plus 7, that will be 63. So 64 will be represented as 100 in octal. I repeat, 64 will be represented as 100. Why 100? Because 8 to the power 2, 8 square, 8 into 8 is 64. So under 8 square we will be having 1. So rest of the digits will be 0. 100 in octal is represented as 64 in decimal. Now we come to hexadecimal number system. So by hexadecimal number system, everything will be defined as the power of 16. So 16 to the power 0 is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So instead of 10, it will be capital A. And then starting from capital A, we will be representing each of the digits as A, B, C, D, E, F. So this will be 11, C is 12, G is 13, E is 14, F is 15. So based on the hexadecimal, we will be having the digits 0 to 15. Since we are starting from 0, it will be 1 less than the number 16. That is 15. 0 to 15 are the different digits that we have. We represent 10 to 15 as capital A to capital F. In some books, you will find small a to small f has been provided for hexadecimal values. It's okay, but we will try to represent in capital case letters, capital A to capital F. So 16 obviously will be represented as 10 in hexadecimal number system. Why 10? Because under 16 to the power 1, we can understand easily. 16 to the power 1 is having 1, and 0 means 16 to the power 0. So over here 10 represents 16 itself. So 10 represents 16 itself. So this is how we can define the different digits in hexadecimal number system. So this is in total the concept of number systems. So let me revise the whole thing. So over here in decimal number system, we start from 0 to 9 because 10 digits are there, and after 10 digits we are representing the same thing 0 to 9, and beside that we are putting 1 in the tens place. As we can understand, units place is 0 to 9, so tens place is again 0 to 9. We can have 0 to 9 because we have the representation based on 10 digits, 0 to 9. Similarly, hundreds place, thousands place, etc., which we actually define as 10 to the power 0, units place 10 to the power 1, tens place 10 to the power 2 as hundreds place, 10 to the power 3 as thousands place, and so on. Everything based on the power of 10. 10 means decimal. Similarly, in binary, we have the representation based on 2 to the power 0, 2 to the power 1, 2 to the power 2, and so on. So we are representing the numbers based on only 2 digits, that is 0 and 1. So 0 is false and 1 is true. So 0 is represented based on 0, 1 as 1. So 2 will be represented as 1, 0, because we cannot represent 2 in binary, because we can represent only 0 and 1. So under 2 to the power 1, we are putting 1. That means 1 into 2 to the power 1, that is 2. So under units place, that is 2 to the power 0, it will be 0, 1, 0. Similarly, 1, 1 represents 2 to the power 1 plus 2 to the power 0. So 2 to the power 1, that is 2 plus 1, that is 3. Similarly, 4 is 2 to the power 2 is 4. So 2 to the power 1 and 2 to the power 0 will be having zeros. So 100 represents 4. So 101 is 5, 2 to the power 2 is 1, that is 4 plus 1, 2 to the power 0 is 1. So 4 plus 1 is 5. So this is actually represented as 8421. 8 is 2 to the power 3, 4 is 2 to the power 2, 2 is 2 to the power 1, and 1 is 2 to the power 0. Anything to the power 0 is 1. So this is the representation of binary equivalents of the decimal numbers that we have represented there. So here 16 will be represented as 2020, because under 8 to the power 1 we are representing as 2. 2 into 8 to the power 1. So that is 2 into 8, that is 16. So under 8 to the power 0 it will be 0. So I am just having a bottom up approach over here so that we can understand it well. So in octal number system we are representing the different numbers as 0 to 7. So after 7 we cannot put 8. We do not have 8 in octal number system. Why? Because we can only represent the digits 0 to 7 in octal number system. So 0, 1, 2, 3, 4, 5, 6, 7. So these are the 8 digits that we have. Similarly, 10 is represented in octal for representing 8. Why? Because 8 to the power 1 is having 1. So obviously 8 to the power 0 will be having 0. 8. Similarly, 9 is 1, 1. Because 8 to the power 1 is 1. It becomes 8 plus 1. 8 to the power 0 is 1. 1 into 8 to the power 0. So 1, 2, 8 to the power 1, that is 8 plus 2, that is 10. And so on. So we can well understand the representation of octal equivalent based on decimal number system. In hexadecimal number system, we can have the representation of 0 to 15. That is 1 digit values in hexadecimal number system, 0 to 15. So 0 is one of the digits that we represent. So 15, 0 to 15, in total we are having 16 digits. Now from 10, we actually represented it in 2 different digits. So we have to represent in hexadecimal number system based on capital A. And we can represent the different alphabets after A, that is A, B, C, D, E, F. Up to F, the 6 digits from 10 to 15, and rest 0 to 9, 10 digits. So 16 digits, 0 to 9, 10 digits, and A to F, the 6 digits. So total 16 digits that we can represent from 0 to 9 and A to F. So here I have given the numbers for your ready reference. So in this particular case, so 10 to 16, since they are 10, 11, 12, 13, 14, 15. So these 6 digits are binary digit values. So we represented the 10 to 15 values as A to F. A to F. And 10 is represented as 16 because 16 to the power 1 is 16. So 1 and 0 into 16 to the power 0, that is 0. So 16 plus 0, that is 16. So this is the whole thing based on a number system. Now whenever we represent the number systems, how will we represent the number systems? Based on the suffix. The new page we are writing 1011, for example. So this is a binary number that we are representing. So based on the representation of the binary number, we have to provide the suffix to make others understand what is the number system of this number, 1011. So if we write suffix 2, so it will provide us with the representation of this as the binary number. Now instead of this, if we write 1011 suffix 10, so as we are acquainted with the decimal number system from childhood, we can easily understand this as 1011. So this is representation of 1011 based on 10 to the power 0, 10 to the power 1, 10 to the power 2 and 10 to the power 3. And when we define it as 2, it will be 1011, that is 2 to the power 0, 2 to the power 1, 2 to the power 2 and 2 to the power 3. So simply the value of this will be 11 and this will be 1011. So two values are totally different. Now over here, if we write the same thing based on 8, so this is another thing. So its decimal equivalent is 11. Similarly, 1011 means, if we quickly decode this, 8 to the power 0, 8 to the power 1, 8 to the power 2, 8 to the power 3. So 1011 means 8 to the power 3. Under this we have 1. That means 8 into 8 into 8. So 64 is 8 square into 8. 8 fours are 32. 3. 512. So this is 512 plus 8 to the power 1 is 8 plus 8 to the power 0 is 1. So 1. So 512 plus 9 equals to 521. So this will be 521 decimal. Is it clear? Okay? Because 0 into 8 to the power 2 will be 0, 0 into anything is 0. 8 to the power 3 is 512. So 8 to the power 1 is 8, 1 into 8 to the power 1 is 8. 1 into 8 to the power 0 will be 1, anything to the power 0 is 1. So 1 into 1 is 1 and 1 into 8 is 8. So 512 plus 8 plus 1 is 521. So 521 equivalent decimal number system, that is the equivalent decimal of octal 1011. And when we will be representing 1011 based on 16, that will be a huge number representing 16 to the power 0, 16 to the power 1, 16 to the power 2 and 16 to the power 3. So 16 to the power 3 into 1, or in other words, we can represent 1 into 16 to the power 3 plus 0 into 16 to the power 2 plus 1 into 16 to the power 1 plus 1 into 16 to the power 0. So that will be equals to 16 square. 16 into 16 is 256 into 16. 16 6 are 96. 9 in hand. So 16 5 is 80, 89. In hand 8, 32, 4096. So 4096 plus 0, 0 into anything is 0, plus 16 plus 1 equals to 4096 plus 17. 4097. 4106. 4116. So this is the equivalent decimal value for 101116. Am I right? So 96 plus 17 is 113. Right? 96 plus 17 is 113. So 4096 plus 17 is 4113. So that is the decimal equivalent of 101116. So if the conversion comes like this, 101116 equals to question mark 10. So this will be the evaluation of the decimal equivalent of 1011 hexadecimal equivalent. So these are the different types of values based on 1011. So I have considered only a single number, but that is represented in different number systems like this. So this is the decimal number system itself. So this is the binary number. This one is the octal number, octal to decimal, and this one is the hexadecimal number. Hexadecimal to decimal. This is octal to decimal, and this is binary to decimal. So this is in total decimal number system converted to binary, octal, and hexadecimal respectively. Now the question is, if we have any other number system, instead of binary number system we can have trinary number system. So how can this be represented? So this can be represented as number system which has a base 3. So this can be represented as trinary number system. So for example, if we have 21, the number system is 3. So trinary number system can be represented with the suffix 3. So what do we mean by 21 in trinary number system? So we can directly put 3 to the power 0 and 3 to the power 1 over here. So this will be represented as 2 into 3 to the power 1 plus 1 into 3 to the power 0. So 2 into 3 to the power 1 is 2 into 3 plus 1 into 1. So this is 6 plus 1, which provides us with the value 7. As simple as that. So simply we can write 213 question mark suffix 10. What is the decimal value of 21 base 3? So it will be 7. Similarly, if we have tetranary number system. So what do we mean by tetranary number system? Tetranary number system means which has the base 4. So if you want to represent 21 base 4 equivalent to decimal number system, so we can just put 4 to the power 0 and 4 to the power 1 over here. So 4 to the power 1 means 4. So that will be 2 into 4 to the power 1 plus 1 into 4 to the power 0, that is equals to 8 plus 1. Because 4 to the power 0, anything to the power 0 is 1, so 1 into 1 is 1, and 2 into 4 is 8. So that provides us with the value 9. So this can be represented as 4 equals to 9 in decimal. So 21 base 4 equals to 9 base 10. So that is the equivalent decimal based on tetranary number system. Similarly, we can also have pentanary number system. If we have a particular number system 16 base 5. So the suffix is actually defined as base. Which base we are talking about? The number system is 5. So we can easily create the equivalent to 1 into 5 to the power 1 plus 6 into 5 to the power 0. Now is this correct? Can we define pentanary number system 6? So when we define a number system as 2, 3, 4, 5, so these are the number systems. So what did we see? We saw that when binary number system is concerned, we can represent the numbers, the digits up to 1 less than this number system. Similarly, in 3, we are having 0, 1, 2, up to 2. We can represent up to 2. So in the previous page, you can see that we can represent 2, 1. We cannot represent 3 in the number system 3. Similarly, in the number system 4, we cannot represent 4. In binary number system, we cannot represent 2. We can only represent 0 and 1. In decimal number system, we can represent from 0 to 9. So over here, in pentanary number system, we cannot represent 6. So this is wrong. So in your interview or in your viva, if this type of conversion is given, that is just to confuse you. So without being confused, we have to say we cannot have a number in pentanary number system as 16. Is it clear? So this can be represented in a number system at least 7. If 7 is the base, then we can represent 16, because 6 is the digit that we can represent at least for a number system 7. That is 1 more than 6. Here, over here, if pentanary number system instead of 16, we give 14 based on pentanary number system, then this one is correct. So how can we decode this? Because from 0 to 4, 0, 1, 2, 3, 4, 5 digits can be represented in pentanary number system. So this is correct, but this one is wrong. Is it clear? So in your viva or in your interview, if this type of confusion is made, then you can directly say, sir or madam, this is not a number based on base 5. Base 5 will be carrying digits which are 1 less than that base at least. So that is how we define this particular code. So obviously, instead of defining that, we can provide this as 14, 5 to the power 0 and 5 to the power now 1. Now we can just write 1 into 5 to the power 1 plus 4 into 5 to the power 0. So that is equals to 5 plus 4 equals to 9. So 9 base 5 is the equivalent of 14 base 10. Is it clear? 9 base 10. I'm sorry. So this is 9 base 10. And this is 14 base 5. We have given 14 base 5. So from 14 base 5 we are converting to 9 base 10. So this is the equivalent decimal of the pentanine number system 14. So this is how we can provide the different number systems. So similarly, base 5, instead of base 5, if we have base 8, we are just defining it as octal number system, and so on. Now let's have a look. For easy decode, or when we want to decode a particular number system to another number system which is connected with some relation. How? Let's have a look. If we have a number system 8, octal. So this octal number system 4 can be represented in binary as 1000. So what do we mean by 1000? So 1000 is represented as 2 to the power 1, 2 to the power 2, 2 to the power 3. So like this, we can just represent 1000. So under 2 to the power 00, under 2 to the power 1, 0, under 2 to the power 2, 0, 2 to the power 3 is having 1. So with respect to 4, 8, that means 4 is represented as 8 in octal. So what will it be? It will be represented as 100, 0100. So in other words, this is actually equivalent 8, 10. So if we want to represent this in eight base 10. So the base of 8 is 10 decimal number system. So 1000 is the representation of binary. So this is in binary. So here what we can see is when we are having 2 to the power 1, this is related to the base 2, and 2 to the power 3 is related to base 8. So what is the relation between the base 2 and base 8? The relation between base 2 and base 8 is we can represent 8 based on 3 different digits at most. So 0 to 7, any octal number can be represented from 0 to 7. So for depicting 0 to 7, we have to have at least 3 different bits for binary. 000 to 111 is represented in binary 0 to 7, which can be implemented in octal based on only one single digit. So similarly, when we define an hexadecimal number. So 0 to 7 can be represented in single digit. So similarly, if we consider a number 16, for example, so how is 16 represented? Decimal base. So in binary, it is represented as 1 binary. So 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4. Under 2 to the power 4, we are putting 1. In octal, how do you represent in octal? 2, 0. So 16 is represented as 2, 0 in octal. And in hexadecimal, we represent 16 as 1, 0. So the relation between the binary, octal and hexadecimal is that this is 2 to the power 1, this is 2 to the power 3, and this is 2 to the power 4. Binary, this is octal, this is hexadecimal. So in this case, what we can define is, if any number is represented in binary, so we can easily convert it to octal based on 3 different bits. If we consider 3 different bits from right to left, automatically we can convert it to octal. So what is 101? 101 is 5. 110 is 6. And 10 is 2. So this is the equivalent octal. So 3 digits in binary, 3 bits in binary, binary digit, full form of binary digit. So in short, we define it as bit. So 101 is 5 from right to left. We are just constructing 3 bits each converted to 1 bit of octal, because 2 to the power 3 is equivalent to 8, which consists of 3 bits of binary. Now if we want to convert it to hexadecimal easily, what we can do is we can consider 4 different bits of binary and consider as 1 bit or 1 digit of hexadecimal. So 0101 is 1 digit of hexadecimal and 1011 is 1 digit of hexadecimal. So what is 0101? 0101 is 5, because in the left portion 0 is not considered, so 101. It considers as 101. 0101 is considered as simply 101. So that is 5. And what is 1011? 1011 means 11, hexadecimal 11. So over here you can see in this number, so 1011 is 11. 11 equivalent is 1011. All right. So 1011 is 11. How do we represent 1011 in hexadecimal? So 1011 in hexadecimal is represented as C. So 10 as B. 11 is represented as B. So this will be the hexadecimal equivalent for 101100101. So 0101 is 5 and left part 1011 is 11. 11 is represented with B. 10 is represented with capital A and 11 is represented with capital B. So this is how we can easily convert from binary to octal or hexadecimal with respect to considering them as 3 bits each of binary converted to octal. So this is the 3-bit 101 converted to 5, 110 converted to 6, and 10 it's considered as 010 converted to 2. Similarly, when we consider hexadecimal, we consider 4 different bits of binary to the equivalent digit of hexadecimal. So 0101 is 5 and 1011 is capital B that we represent in hexadecimal. So the equivalent of octal is 265, that is the equivalent number of 101100101 binary, and B5 is the equivalent hexadecimal value of 10110101 binary. So this is in total how we can easily convert binary to octal and hexadecimal. Now let's have a look how we can consider the tetranary number system. Tetranary number system is 4. Any number whose base is 4. So that can be represented as 2 to the power 2 equals to 4. So any 2 bits, if we consider 2 bits of binary, that will be the equivalent of 1 digit of tetranary number system. So this will be, if we consider from right to left, 01 is 1, 01 is 1, 11 is 3, and 10 is 2. So this is the tetranary number system equivalent 2311 based on 10110101. So as we saw in the previous 10110101, 265, this we have already evaluated in octal, and in hexadecimal we have already evaluated this based on hexadecimal. So this is based on the relation of binary number to the tetranary number system, that is base 4, (265) that is the octal number system, and B5 that is the hexadecimal number system. So binary converted to tetranary number system based on 2 digits each, 2 bits each, because 2 to the power 2 is 4, so power is 2, so we will consider 2 bits each. 2 to the power 3 is 8, so we will be considering 3 digits, 3 bits of binary converted to 1 digit of octal, and hexadecimal is 2 to the power 4 equals to 16. So 4 bits of binary will be considered as 1 digit of hexadecimal. So this is the logic that we play based on conversion of binary to tetranary, octal or hexadecimal number system. But we cannot do this, the same rule cannot be applied for other number systems. Why? Because they don't have a relation based on the power of 2. So all of these are power of 2s. That's why we can convert them easily with respect to the different 2 bits, 3 bits or 4 bits respectively for tetranary, octal and hexadecimal number system. So if we want to convert a particular binary to hexadecimal, binary to hexadecimal, this is the way out. Now when we want to convert a particular decimal number system to binary, or decimal number system to octal, or decimal number system to hexadecimal number system, the method will be different. So that is simply division of the number based on, for example, this is the binary number and this is the decimal number system. So how can we represent this as binary? How can we convert the decimal number system to binary? So what we have to do is we have to divide it by number system that we are asking for conversion. So 2 is the divisor and 10 is the dividend. 2 5s are 10. So here remainder is 0. This is the remainder. Again we divide it by 2. 2 2s are 4. Remainder is 1. 2 1s are 2. Remainder is 0. 2 zeros are 0. Remainder is 1. So the rule is we will keep on dividing it by 2 until and unless we have a quotient 0. And then we will just read out the remainders upside down. That means it is following a stack data structure where we are popping the different elements which are pushed at the end of the stack, the remainder stack. So it will be 1 0 1 0. So we will be writing it upside down. So 1 0 1 0 is the equivalent binary with respect to 10 octal, 10 decimal number system. So this is the decimal number system. So 10 decimal number system, this is the equivalent binary. So this is how we can convert decimal to binary. Similarly, if we want to divide or find out the equivalent octal, then we have to divide 10 by 8 until and unless we have a remainder 0. If you want to convert it to hexadecimal, you have to keep on dividing the decimal value with 16 and so on. Just follow my next video, which will be converting the different decimal number systems to, we will take some other examples of binary, octal, that is decimal number system to octal, decimal number system to hexadecimal, or decimal number system to other number systems. How can we find out the equivalent of those number systems with respect to a decimal value by dividing by the number system value? So we have that video in the next video. Bye for now. Thank you.